Hello, my name is Diego, and I'm going to present these slides based on the article called Input Impedance Analysis of an LCLC type capacitive power transfer converter. The slides are going to be divided as follows. First, I'm going to explain the motivation behind this, the topology and the prototype we built, and the input impedance analysis. I'm going to finish the presentation showing some simulation results and experimental results and giving some conclusions. The motivation behind this is that CPT systems are a novel alternative to traditional IPT system that uses the magnetic field approach. Now they use this electrical field approach, and with this, they can be built in a way that the misalignment of the wireless power transducer affect less the power delivered to the load. So they are suitable for applications such as electric vehicle chargers, and also not using magnetic field, it'll avoid some losses, for example, due to eddy current losses. There are several compensator filters topologies for this type of systems, and we choose the LCLC one because it has some characteristics. For example, it can deliver more power to the plates, to the transducer, as a consequence, more power to the load. And also it helps to downsize the inductors. And with this downsized, we will have less resistive losses, and also we were able to study PCV inductors. So we make two analyses of the input impedance of the LCLC filter. We first make the assumption that the capacitance C was way much smaller than C1, the capacitance in the transducer compared to this one. And the model result is the one shown in orange, and with this model we can find only two bifurcation frequencies. And then we include capacitance C, but we make the assumption that the load was the resistive load was high, so there were low power being delivered. And with this, the model in blue show an additional bifurcation frequency, so we need all of the parameters. If we include also the resistive load to the model, we can find for high power rates delivered to the load an additional bifurcation frequency. And with this bifurcation frequency, we make the simulation of the circuit complete, and we find that, of course, when there is bifurcation, there's more current being delivered in the input sides, and also more current in the output. So we will have maximum efficiency with maximum power rates delivered to the load. We make a low power implementation, and as it is a low power system, only 3 bifurcation frequencies are going to appear. So in orange, you may see the data took from the converter, and in blue the model. We have an error around 6%, and we should mention that the displacement is also due to the resistive losses that were not included into the model. To conclude, so the solution of the input impedance is presented using all of the components. All of the parameters needed to be included if we want to determine all of bifurcation frequencies for high and for low power being delivered to the load. An advantage is that at these bifurcation frequencies, we encounter that we will have not only maximum efficiency being delivered, but also maximum power delivered to the load. A disadvantage is that the solution, there is no analytical solution as it is an 8-degree polynomial expression. But if we found the solution, if we make the computation needed, we can close the loop and always deliver maximum power to the load for systems, as I mentioned before, electric vehicle wireless charging stations. Thank you very much for your time, and I look forward to hear some comments from you.